We're going to talk about how applications get developed, how infrastructure that supports them have evolved, and just the entire software development lifecycle. We'll see how microservices, containers, Kubernetes, and Azure all fit into this picture. So about me, I'll start with a bit of just a fun detour and also try to let you know more about me and also share why I wanted to share this knowledge, share my knowledge on this topic. To start, I'm a systems level person, so even my current title includes the term systems. It means that I focus on inputs and outputs and on how components get put together, and also on how to best leverage technology and resources to accomplish business objectives. I have some of my favorite icons of my favorite tools on the screen. Daily, I'm using Azure and Visual Studio, Azure DevOps, and GitHub, Microsoft Fabric, SQL Server, Python, .NET. These have been the tools I've used for years and have informed how I design systems and the advice that I give to the organizations I've worked in. There we go. So I gained a passion for modeling information systems during my work as a computational physicist on the CMS project at CERN. I worked on the LHC, the Large Hadron Collider. I split my time there measuring collisions at the detector in France over on this side, and then analyzing the data back on the main campus down here in Geneva, Switzerland. We were proving the existence of the Higgs boson, which was an important piece, or is an important piece, of the standard model of particle physics. And that work ultimately did lead to a Nobel Prize for the theorists that predicted the Higgs existence. The LHC, this giant loop, accelerates protons near the speed of light around a 17-mile track to collide particles with energies that literally rival the Big Bang. This is a picture of the detector that I worked with, called the CMS, or compact muon solenoid. It was a really impressive experiment. You can see a person down here for scale. And what was also impressive was the computational technology required. Here's what a collision looks like visualized from reconstructed data. And there's a lot of data, and a lot of scientists all over the world trying to analyze it at the same time. These collisions could produce up to 40 terabytes of data per second. So a lot of work had to go into filtering the data just to be able to store it, process it, and access it. To make it possible, to essentially make computing work at such a massive scale in the days before cloud providers, the CMS project constructed its own distributed computing system that spanned institutions across the globe. Data is created and stored across tiers of facilities, so different types of information can be queried from each tier. This helped ensure no one facility was getting all the traffic, and that queries could be run as close to the user as possible. When I think back on it with my perspective today, I'm amazed at how this problem of load balancing and capacity optimization has evolved over time. To perform analyses, we had to schedule jobs on what was called the grid service, and that service would determine the correct tier. It would submit the jobs. Those jobs would go away to some other site and run there, and then come back with the results as they became available. This distributed computing method enabled thousands of individuals to be running really CPU-intensive queries across huge amounts of data all at the same time. And since my time there, the operations team supporting this infrastructure has continued to innovate its distributed computing practices, going so far as to actually include Kubernetes. Let's see if I can pull this up here. So CMS is compact muon solenoid. And they've come so far as to be able to offer this. Well, you can't really run it yourself, not easily, but they've done this for their own practices, and it really has inspired me quite a bit. And now, this brings me back into kind of into full view here, where I not only wanted to provide you a fun and interesting intro, but I also wanted to try to inspire you to think about how IT scales infrastructure to meet some of its most taxing demands. Using the programming skills I learned at CERN, I moved into software development at a couple of tech companies and eventually got involved in data engineering, operations, and even working with clients. That led me to my current role, where I lead cloud and data architecture projects for Oregon's fourth largest city, the city of Gresham. I lean on these experiences when I'm considering how to modernize and scale both infrastructure and culture around an organization's software practices. So thank you for joining me as I try to share with you what I've learned. Which brings the discussion to, shifting to cloud native with Azure Container Apps and AKS. Essentially, how do we implement modernization, like embracing the cloud, and understand which tools in the cloud we should be using to do it? So a key part of this presentation is talking about the shift, right? We're going to discuss how IT has traditionally strategized around software development and how those investments have made it kind of difficult to move applications to modern tech stacks that have better scaling options, developer experiences, and built-in telemetry. And what are we shifting to? Well, we're shifting to cloud native architecture. Cloud native is an approach to designing, building, and running applications that fully leverages the scalability, resilience, agility, and automation offered by modern cloud platforms. We'll get into how those terms appear in cloud native tools. If you started development projects from scratch in the past 10 years, you may have found it simple to get started in the cloud and could already be fully embracing cloud native. But if you're still reliant on traditional software development practices that deployed monolithic apps to virtual machines, you might still be wondering how you can switch to this new cloud native world. And of course, we're going to talk about Kubernetes and container apps and how Azure does cloud native. Switching to this world of containers and microservices can feel like a big change, which is why I thought it could be worthwhile to make it a topic for our group. Now, I'd love to know a bit more about the audience that I have here's general knowledge on the topic. So with just a quick raise of a hand or a type in the chat, let me know if you're familiar at all with containers, Kubernetes, or even container apps.
So we've got a question. Brendan's got his hand up.
Oh, no, I was just saying I'm familiar with those.
Yeah, absolutely. Yeah, keep your hand up if you're a Kubernetes expert, so that way we can make sure we involve you in answering other questions.
Yeah. Though container apps is new for me. So.
Yeah, well, and it's got a lot of potential. I'm excited to talk about kind of how it fits into your different options for trying to use containers, trying to make this shift. So thank you, Brandon. All right, let me pull this back up here. And next slide. Okay, so just real quickly here. Excellent, Scott. Great to know that. So basically, this leads us with those three things to here what our objectives are. We want to become familiar with these cloud native concepts and the benefits. We want to learn how to build cloud native solutions in Azure. And if we have time, I'll try to explain how you might migrate some traditional workloads to tools like Azure Container Apps and AKS. But to start, let me try to just give a little background to the concept of cloud native itself. So cloud native has been around for 10 years now. So it's one of those things where software teams ask themselves like, well, are we doing cloud native? Are we cloud native? So let's talk a little bit about what it means to be cloud native. So the cloud native is led by the Cloud Native Computing Foundation, which was started back in 2015. And you can kind of see like all these projects along the bottom here that they've been kind of involved with or taken inspiration from, right? Like we're kind of seeing this evolution of our application stack. And essentially, it's built on decades of open source and open standard development. And the CNCF landscape has been curated from contributors that were directly involved in these projects. A shining example is Heroku. If you ever deployed to Heroku, it was one of the first and most notable kind of like easy buttons for deploying apps. You just said, here are my files, and it kind of took care of all of it. Fast forward today, and now there's like 1,000 easy buttons, and knowing how like what order to push them all in is kind of what we're going to talk about today. So this landscape has grown to encompass a wide variety of technologies and contributors, and the CNCF has even published a landscape and a trail map to help vendors and software purchasers understand how far you are along what's called the cloud native maturity spectrum. So I think There it goes. I kind of like looking at this when I think about cloud native. So they published this landscape. I mean, this was actually kind of a few years ago. Cloud native is no longer talked about with as much hype of like AI and stuff like that, but it's still really important to how like application innovation has become easier to do, right? And so we're going to talk about some of these concepts, specifically containerization and orchestration, and we're going to talk about how to kind of fit these things into a tool. And speaking of tools, that's kind of where what's called the CNCF landscape comes into play. And you may have seen like these types of images before. This one's actually hosted by CNCF itself. And really what it's doing is it's just showing you, okay, here are all these projects and products that are participating in cloud native, right? And they even have this stats here to kind of show you the like evolution of how a project or a product might become cloud native, right? So they have these concepts of like it's a sandbox or it's incubating or hey, it's graduated. And we're talking, these are the big names that have done these things, and we'll talk about some of these things today. But it is really a whole community that has embraced open source and open standards, and it's been really responsible for helping the software industry make smarter technology choices. And organizations' ability to adopt the principles that cloud native talks about is a core part of what it means to be cloud native and to participate in cloud native. Okay, so now if you look at the resources from the Cloud Native Computing Foundation and then cloud providers like Microsoft, you'll find that there are features that are common to cloud native endeavors, or so-called like pillars of cloud native. And you'll find these ideas expressed in different ways. Sometimes more abstract terms are used like operability, observability, elasticity, and agility. Others say you have to mention immutable infrastructure, declarative APIs, CI/CD is really important. And of course, there's like a critical role in cloud backing services since these are made to be in the cloud. And also the private cloud, by the way. We talk about the kind of the public cloud, Kubernetes, and a lot of these cloud native tools, they're built to be kind of like cloud aware and to be able to essentially just mount cloud resources into a cluster and use them as if they lived there. So I'm going to focus today on microservices, containerization, and orchestration. I think that they're really simple ideas and they capture what we need to do to be cloud native. And they're also kind of used to build up the capabilities such as resilience and resource optimization. So one last thing on this, notice we haven't really said anything about using specific cloud services. Instead, this architecture embraces operational patterns that naturally take advantage of the key capabilities of cloud computing, namely the dynamic nature of cloud infrastructure. And so this is where we really start to understand what it means to be doing cloud native application development. We're going to be taking advantage of that dynamic nature of cloud infrastructure. What we're basically going to do here is we're going to compare traditional software development lifecycle, and we'll see how cloud native has impacted the evolution of the software development lifecycle and where microservices, containers, and orchestration comes into play. So of course, everything starts with the dev. They have their own operating system and their own IDE, their languages and their libraries, and finally, their app code. And traditional apps hosted on VMs tend to be created as monoliths, which mean that they're tightly coupled. So monoliths mean that all of the services are tightly coupled sometimes into even just a single code base, right? And the applications, they get deployed to VMs, and the VMs require manual setup of the operating system, and also they need to have the language libraries installed and need to configure any runtimes that might be specific to the application needs. This type of deployment in the traditional software development, it necessitates like a detailed understanding of how the code integrates with the server environment. And you have to ensure that the appropriate runtime is present to avoid errors. You have to ensure your app code and also your environment variables. Yeah, so it's a lot. At this point, your deployment efforts take up as much or more resources than your actual application does. So when you move to an architecture that allows you to focus more on your application than on your infrastructure, well, that's a key way that cloud native practices can reduce tech debt and they enable innovation, right? And scaling, it's going to pose another challenge because, well, if one part of the app, for example, just the reporting section, needs more resources, but it has to share a VM with all the transactional modules, well, the development team has no choice but to ask for a bigger VM or to implement some type of load balancing and spin up essentially a second copy of the app, which means we're using a whole nother infrastructure stack here, the VM, the OS, all of this configuration. And so we're not being very efficient. We're essentially saying we need an entire computer for our application, right? So these types of problems, this mashup of development and operations, it makes it difficult to build great products and to adapt to new technologies. And honestly, it can make it difficult to attract staff that are savvy on modern tooling. The cloud native architecture was created specifically to tackle these thorny software development lifecycle problems. So understanding how to leverage these principles is a key way that we're going to be cloud native. So let's go ahead and take a look at these. So again, it all starts with that developer. And for a moment, things kind of look the same. The first responsibility, of course, is to break our monolith into the microservices. So microservice development involves designing the application as a suite of smaller, independently deployable services. And each one runs its own processes, and if they need to communicate through each other, it's just expected that they'll use something simple and understood like HTTP endpoints. What we're going to see is that these principles are used in higher levels of the cloud native stack, specifically in containers and in orchestrators. And microservices is a really important thing to make this possible. So, in our example, what we've done here is we've just broken these into their own services, and these might become multiple containers, each one themselves, which we'll see in a second. Each service then would be developed and deployed and scaled independently without impacting the rest of the system. So if we no longer need to scale entire apps together and have whole teams coordinate on app deployments, well, then we can focus on individual pieces of functionality. We can develop them faster. They don't all have to be developed in the same way. And if we can when we put them in the cloud, we'll be more ready to take advantage of the disposable nature of the cloud. Remember, I said to be cloud native, a lot of what you're doing is taking advantage of the fact that things are ephemeral. If you have to deploy an entire VM with an entire operating system, there's no way to scale that to zero. And we'll see that when we talk about the differences of Kubernetes and Azure container apps, right? If a VM's involved, you have a constant workload running. And so this is a part of what we're doing is we're no longer using these entire machines. And to do that, we're breaking things into microservices, right? So to talk about what we do with those microservices, we put them into containers. And unlike VMs, which virtualize that entire distinct operating system at a hardware level, we're talking containers and container technology. They virtualize at the operating system level. And so this is called the type 2 hypervisor. And by virtualizing at the OS level, they are able to share components of the kernel rather than each individual container needing the entire OS. So they share, and they don't share hardware like we do over here, they share an OS, right? So we're able to reduce having the larger machines, and a single app, or multiple apps rather, can fit onto that single machine. And they're able to have process isolation through just classic concepts that come from Linux, like namespaces and C groups. And so going back to cloud native and that whole evolution of things, we're taking advantage of what we've learned, of what's present in technology that exists at the lower levels to abstract them at the higher level, right? And containers are really flexible and reliable because they aren't just code in a folder like we saw in our traditional deployment. They become what are called immutable objects. They're container images. And the container images is a single standalone artifact. It includes everything needed to run a piece of software: the code, the runtime, the libraries, environment variables, configuration files. It's the main reason containerization solves the problem. It worked on my machine. It's solved because only a single file is required to build your image, and all that is needed to run it is a container runtime, the most well-known of which is called Docker. So in Docker, you can use this container runtime Docker to build your image, and then you can publish it up to a container registry, such as Docker Hub. And once it's up there, it can be pulled and used in other places other than your machine. Once again, that solves that "it worked on my machine" problem, right? And if you're going to deploy it to Kubernetes, well, you get to use those images in your Kubernetes deployment and Azure Container Apps. So we've kind of moved away from having to have these unique bespoke deployments to having these imperative deployments, or to these declarative deployments that use a Docker file to describe, okay, here's everything you need to run this application. And if you need to scale up, well, rather than needing to redo those imperative deployments like we saw over in the traditional side of things, well, we can simply just run more copies of the containers. And the container runtime Docker, it just knows how to spin up that exact copy in its own isolated namespace. That means we can mix and match workloads, and other developers can use the language and libraries of their choices. They're not language and library for a whole OS. It's just those languages and libraries in that small container. And we even have these new deploy capabilities that mean that we no longer have to deploy the entire code. Now we can just deploy one service at a time as they have updates. And that means, of course, that we're going to be able to really divide and conquer for our teams. So maybe the front and the back end teams no longer need to coordinate on deployments of the application. Now they can just separately do it, and if you need more back end containers to support the load, well, you put more back end, or vice versa for the front end. And also, if you want to do something new like AI, well, you're not just attaching it into this giant monolith. Now it's just going to get developed in its own container. One moment. Okay, hurrying right along here because there is still quite a bit to cover. This takes us to the topic of orchestration. So orchestration is how we manage all these containers to make scenarios like this possible. Without orchestration, teams would have to individually start and monitor and scale hundreds or thousands of containers, which is both error-prone and inefficient. Orchestration platforms like Kubernetes, for example, automate these tasks by encapsulating all of this application infrastructure behind a simple and consistent API that both developers and the system itself uses to manage the containers. So you can see here that's being written as the Kube API server. On the command line, we're using something called kubectl. But it's that exact same Kube API server that is going to, through the use of controllers, actually manage this entire infrastructure. Get a few controllers on there. Okay. So we have that concept of the Kube API. With that, software teams don't need to worry about implementing things like their automated deployments, how they're going to fit their applications onto their infrastructure so that way it most efficiently takes up space. That's called bin packing. Orchestrators are able to enable service discovery, which is critical in a microservices world, load balancing and scaling. We don't need to worry about those things on the software side of things. Instead, the orchestrator kind of makes them first-class objects that are baked into this cluster and are available through this Kube API. In the cloud, this becomes even easier because the orchestration tools are completely managed. For example, the components of the Kubernetes control plane and the system nodes. So here is our first node pool in a cluster. That's an important concept, is your node pool. And the system nodes are responsible for actually managing what happens in the cluster. And a great thing about AKS, and actually a lot of cloud providers, is you don't actually have to pay for these components, right? You just pay for what are called the user nodes, and those are where your actual containers are deployed into what are called pods. So within the user nodes, our containers actually live in pods. And what's interesting is that a pod is the smallest deployable artifact in Kubernetes, right? So you're not actually deploying a container, but a pod. And a pod is this concept that groups containers together from like a networking, local storage, and scaling perspective, which of course is exactly what's needed for microservices deployments. Containers in the same pod communicate with native inter-process communication and share a stable IP address and hostname that are assigned to the pod itself. Right? It's almost kind of like over in here when it's just working on your own machine, it's just kind of living in this type 2 virtualized space that's sharing these resources, yet still being able to be isolated. But now we've gone up a whole level, so that way all of our containers, maybe like something that might be deployed together to support a single service, they'll go into a pod. But it's okay to just have a single container in a pod as well. And one point that I wanted to make here is that pods, you don't just like set them up necessarily by like on the command line like you can with Docker. There are ways to tell this system node here through these components to schedule the pods, and they work across these things here. We'll talk a little bit more about these. But basically, the idea is that that the pods are able to be described by a manifest file, right? So here we've got our developer, they're using that kubectl, they have a manifest file, and that manifest file is going to go into the system node, get stored in this etcd database, and then the scheduler will use it to say, well, hey, this is how my container should run. And the kubelet will help make sure that those pods are actually deployed, and the kube proxy is responsible for helping them all talk to each other. So that's really the point I wanted to make here, is that the pod manifest is an important concept. And then moving up to other important concepts, if I can get this to come back. Yay, I did. Okay. Is a service. So a service is a method for exposing one or more pods behind a single endpoint, which allows applications and services running in containers to easily find and communicate with each other. Rather than one pod needing to figure out how to talk to another pod, or for you to come in and say, I need to talk to both of these pods, like for example, if they're contributing to a replica set, right? So we're just two front-end pods. This might be so that way traffic could be load balanced against them. And what we find is that what a service does is it actually assigns the stable IP address and DNS to that service object rather than the pods themselves. And by doing that, it kind of abstracts away the complexity of the fact that pods might be ephemeral. If one of these containers runs into an error and it says that it's no longer able to accept traffic, or maybe it has even died, well, your controller manager here is going to work with all these other components to say, hey, I need to make sure that there are always two pods for the front end running. All right. So just to reiterate some of the things that we just talked about, internally, Kubernetes is using this kube proxy to manage the network routing. And when the traffic reaches, it doesn't go right to the pod. Now it's going to go through this service first. And because it reaches that service, the service knows which pods are a part of it, and it can automatically round robin load balance to those services, right? So that's kind of a way out of the box. We'll look at this a little bit more with some examples, but it's kind of a way out of the box that, we're not designing load balancing. We're actually just going to use it out of the box of Kubernetes with these orchestrators, and we're going to see that they can just be defined in the manifest file. So furthermore, we're kind of just talking about how traffic gets load balanced internally. We have this cloud controller, right? And that cloud controller is a part of every AKS cluster. And what it enables is for us to use the cloud resources as if they were native parts of our cluster, and to also just like kind of abstract away everything that's coming in here. So if it's running on Azure, it's running on Google Cloud or AWS, right? Like your Kubernetes deployment, it's going to look like any other Kubernetes deployment. So for example, if you needed to not only make your service available internally, if you wanted to make it available externally, we just changed that service type to be called load balancer. And then no matter which cloud you're running, the cloud controller knows how to provision a managed load balancer for you to use to access those pods. So really cool, out of the box. And we'll try to take a closer look at that in just a second with our demos. And finally, probably the last most important thing to mention is this, this little refresh button here. And there's this concept of what's called a reconciliation loop that continuously runs, that compares the current state of the deployments to the manifest definitions that you've provided. They get stored in the etcd database, and then the controllers and the schedulers know if any pods should be deployed or restarted, right? And that's basically what enables self-healing. And it's what makes orchestrators like such an important role in cloud native architecture, when you have all of these services, all of these containers, and we're trying to take advantage of that dynamic, ephemeral nature of the cloud. We're able to spin up resources in seconds now, as opposed to putting in a ticket for our admins or ops teams to spin up a new VM for us. And we got to talk about how we're going to load balance across the two too. No, now you just deploy this, and using baked in concepts, you can have those as first class application objects. So hopefully it's clear in this model. We're talking about more than just using the cloud. We're talking about optimizing that entire software development lifecycle. And also, we're not throwing away anything we've done before. We're learning from it, and we're abstracting those lower level infrastructure to allow our developers to target the higher level abstractions, and they have the dynamic hosting requirements automatically baked in. So
I love this diagram, by the way, Lee. It really helps me understand, like, even just from like a traffic point of view of how much orchestrations happen, even just from like the load balancer piece, right? And like how agnostic that can be. And just all the minutia involved for just making the orchestration across Kubernetes, all these like the nodes and the pods really starting to make sense. And I've never even understood it at this level of granularity. So thank you. This is awesome.
Great. Yeah, I'm glad some stuff is making sense. Admittedly, this is a dense topic, but it's solving some really big problems. And actually using it is actually really simple. It's just like actually seeing all these things can be overwhelming. I mean, when you start talking about the different networking options and like what an overlay network is, and you bake this into your existing virtual networks to manage your node IPs. I mean, you haven't necessarily like, by using an orchestrator, you haven't necessarily saved a bunch of costs, and you may not have even have like saved complexity. Like you're not doing things necessarily simpler everywhere. But the two things that really come with this are your resource optimization. We talked about that bin packing, we talked about that load balancing. in the old days, when you set up a server in a data center, like you start getting those charges right away from power and cooling and all those other things. And it's really up to your ops team to figure out how to optimize that capacity in there, right? Imagine how powerful a tool like Kubernetes is, which just comes along and says, oh, I can just do that for you out of the box. Just tell me, how many replicas you need of this. And if your node 1 is too busy to support your second front end pod, well, I'll just deploy that part of the replica on node 2. And you can scale this out very far. So, and again, the fact that cloud natives is having us like make it so that way our practices are able to kind of look the same in every cloud is really awesome. So, okay. So we're going to move into AKS, and we're going to now like talk about orchestrators. We're going to talk about Azure Container Apps. But before we do, I do just want to briefly talk about, how do we traditionally scale in Azure, right? We just saw that picture of the orchestrator, load balancing, and everything. And so I have a picture here that kind of shows what we do here, right? And this comes from, let me see, can I click on that? This just comes from the Microsoft Learn documentation. Going through stuff like this can be really helpful to understanding all the different things that are available. It's admittedly, with the addition of things like Bastion and SNAT, adds a few more pieces, but makes a couple of other things simpler and definitely more secure. But here are the things we're doing to do load balancing in Azure. And if I'd had time, I wanted to actually do a demo here, but we'll save the demos for container stuff. Really, we're managing our capacity in the traditional way, right? You can kind of see we're still spinning up these full VMs. We're still applying rules and scripts at that entire OS level, just to make sure our code is more available. We don't get the built-in self-healing, although we do have health probes to let us know which VM is available, right? But if the VM goes down, well, we need to make sure that we redeploy our application to it, spin it up again. We still have so much to configure at the infrastructure level. We haven't even talked about like what do we do with service discovery, right? When you use the Azure load balancer with backend pools of VMs, you do get some great benefits. Like I mentioned, the health probes, periodically checking the availabilities, and if the VM fails, well, it's not going to send traffic to that VM. It'll go ahead and send to the next one. It's that same kind of round robin concept that we're using. And with this type of infrastructure, you absolutely can get a high availability and you can prevent your downtime. But you still have to manage things like your load balancing rules and decide if you're going to have a NAT gateway or if you can use the SNAT that's built in. But those rules need to be there to define how incoming traffic is distributed and kind of like how to use the front end IP that you need to build. And it can be a lot to do this. And it needs manual intervention. There's definitely risk of misconfiguration, and managed services like Azure Web Apps and Azure Application Gateway do help, but you're still solving the resource optimization problem rather than it just being baked into your app platform. So we're going to switch now back to the cloud native world of Kubernetes, but just keep that in mind as we go through talking about like what cloud native had to learn to be able to know what to implement, right? So let's take a quick look at our AKS components. And at this point, I've got this slide here just for some overview information. And then on the next slides, we'll actually start going and looking at a cluster in Azure. So about these components, this picture here we'll talk about more in a second, but really we're talking about our cluster right here. That was the main part of my diagram. And this, by the way, this is from the Azure Well Architected, and we'll talk about what that means for what I'm demoing in a second. But just to briefly go over these things, right? So we're not doing that traditional resource optimization in Azure. We're being cloud native. We're not just like taking what we used to do in the data center and then doing it again in Azure. No, now we're going to, in Azure, use the components of ephemeral easily created infrastructure, right? So for example, our cluster. So the cluster has the system node with the VMs, but these can be managed. The system nodes themselves are managed. Like I mentioned, you actually don't even pay for those, but you can choose a higher tier that you do have to pay for, and that can make your availability options go a bit further. But the control plane includes like the Kubernetes API server and the scheduler and the controller manager. They're provisioned, patched, and scaled by themselves, right? It also manages, this is also where the etcd data store is managed. That's a critical component of the high availability. And then in these node pools, right, you still have to deploy your VMs. You still have VMs and scale sets that need to power the nodes, but your code doesn't have to touch those parts of the infrastructure. In fact, if you do need to spin up VMs to support your user nodes, but if based on how you set up your cluster, you can actually use what's called node automatic provisioning to dynamically provision and scale your user nodes. And so they become managed kind of just like your system node. And there's even now an option of creating your cluster in what's called automatic mode, which, as the name suggests, automates like pretty much all the operational tasks involved in managing your cluster. It has that node auto provisioning, and then it also becomes pre-configured with like security, networking, and monitoring settings, your automatic upgrades, and auto repairing your nodes, right? So we're getting, as time goes on, we're getting more and more capabilities of our cloud tools to not focus on our infrastructure. Talking again about the bin packing, that's not something that we have to figure out anymore. Kubernetes natively handles it through its intelligent scheduling algorithms. It assigns the pods to the nodes based on the available resources, like the CPU and the memory that all the pods are sharing. And the Kubernetes schedulers evaluates the resource requests and the limits that you have specified for each pod. We'll see those in some manifests in a second. And it finds the optimal node where the pod can be placed. So that way you're not overcommitting resources. And another thing that's managed is the load balancer. Load balancer, like we talked about, load balancing is achieved using services. The services kind of provide that stable endpoint for routing your traffic to the pods as they come in and out of existence. When you expose pods as a service, you create those stable endpoints and you ensure that the traffic gets evenly distributed among the pods. When a service of type cluster IP is created, it gets its virtual IP address, it means that it is going to be used only within the cluster. And the kube proxy component that's running on each node, it maintains the routing rules so that any request to that service IP is automatically forwarded to one of the healthy pod endpoints, back into that round robin mechanism I mentioned earlier. So for external traffic, I mentioned that load balancer, but you can also use what's called so that's like a service type. I mentioned you just declaratively state it in your manifest. So you'll see service type load balancer, but there's also one called node port. And they work kind of differently, but load balancer is probably the one that you're going to end up using down the road. And you can even add on further ingress controller options to add that load balancer. It operates at that layer 4 level. Well, if you need other things at the layer 7, that's when you can add on those ingress controllers. So we're also managing fault tolerance. The native fault tolerance comes through that combination of the self-healing mechanisms and the intelligent scheduling. If the pod or a node fails, the control plane automatically detects the issue through that reconciliation loop, and it works to replace or reschedule the affected pods on a healthy node. And basically what it's doing is it's always just trying to make sure that it reaches the desired state that you specified in your manifest. So also scaling. We'll talk a little bit about the horizontal pod auto scaling. Basically, that's just a way that you're based on CPU utilization or maybe memory. Your application can dynamically adapt to a workload. It can scale up during high demands, and then it'll scale back down during the low periods. And you just really have to specify those metrics, right? Like you're not saying like, oh, I I better make sure when it's a busy time of the year or my application, the people using my application are responding to some urgent high activity, well, you don't need to like intervene with that. You can just set those thresholds and the HPA will kick in. And I mentioned, I was talking with Greg just a moment ago about how complicated the networking can get, right? And it has its own story too. I'm not sure if I really actually want to go too deep into the slides and stuff I have prepared here, but suffice it to say, there's managed components of those two, right? And they can be used to enable persistent storage and make different type of ingress and egress functionality possible. So I'll just quickly show the slides here. Historically, KubeNet has been the default networking option for Kubernetes, and basically it was worked really well because it kept its IPs of the pods separate from the pool of IP addresses that your nodes were running on. And so that meant that you didn't get that IP exhaustion, but it did lead to like a really much more limited integration with other Azure services. And so Microsoft did create what's called the Azure CNI, the container networking interface. And in these situations, the pods receive the IP addresses from either the same virtual network as your nodes, or more recently in the Azure CNI overlay, from an overlay network itself, right? And so that kind of shows what this overlay network here is. And all this stuff, it really just goes up to show that, an orchestrator is responsible for a lot, but they're the things that they're the pieces of the software development lifecycle that are least relevant to your application, right? Deploying the underlying infrastructure, optimizing your capacity, ensuring the applications are available. Instead of doing that, you're focusing on the most important parts of your application. You're writing the code, and now you're building the containers and publishing them to the registry, and you're scheduling them on the pods using the manifest files, right? You're not descending down into that world of load balancing and bin packing. It doesn't mean that Kubernetes is simple, and it doesn't mean that you don't have complexity. I think I mentioned just a moment ago, Kubernetes is really good for that capacity efficiency, but it's also really good for that abstracting up the infrastructure stack for developers, right? So in our demo, we're going to look at the simple standalone clusters that kind of just to illustrate the cloud native concepts. But in a production scenario, you should definitely spend some time reviewing the Azure architecture documentation. They've provided this baseline reference architecture that follows the Azure well-architected best practices. And really, this is what we'll need to implement a real-world scenario. And this is where my picture kind of comes from, because Kubernetes isn't just going to exist on its own. It's probably going to fit into like a hub and spoke topology. And there's a lot of considerations that come with that. So I'm not like meaning to imply that, the shift to cloud native and Kubernetes is necessarily easy, but it maybe does hint at why something like Azure Container Apps exists. So that's maybe a little preview. Okay, so demo time. So let's talk about the cluster, the control plane, and the system nodes. So I've got some commands here for us to create the cluster in two modes. So this top one here is kind of just like the default that you're going to have. And then I mentioned that you can also create it in automatic. So let's go ahead and take a look at those two. So we'll start with my default one here. So we'll go into the Kubernetes service, and we got this. And hopefully some of the things that I show here are going to look familiar for what we've been talking about. So specifically, we talked about the node pools. So this isn't the auto. So we're going to see our node pools here. We're going to see the nodes that come with it. And here I mentioned node auto provisioning, but that's not configured here, right? And if we go into workloads, right, we'll be able to see kind of the things that are deployed here. And many of these actually come out of the box, right? These pods are actually a part of what's called the kube system namespace here. And so they're back in our picture of that control plane that had the controller manager. Those are built using Kubernetes itself. Those components are deployed to Kubernetes using Kubernetes, right? And so we have these pods that are actually managing all of those components of our cluster. It's really cool. And I do have just a quick demo to show, but this one is not connected to this one. We'll use the other one. So next, let's go ahead and switch over and just quickly look at what it looks like in auto. Let's see if I can get these two next to each other. Really, the difference between auto and regular is what we're seeing here in our settings, right? In the regular Kubernetes, right, our standard Kubernetes, we see our node pools, we see, how we're upgrading those nodes, we have a security configuration. Over on the auto side, our cluster configuration, it's just these two things, and all of the upgrades are handled. Your security configuration automatically chooses the Microsoft Entra ID with Azure RBAC. Those are really important concepts in Azure, but we won't go through them today. And yeah, so you can kind of also see like the differences here. So I deployed this one specifically using KubeNet, which by the way you can't do easily anymore because they want you to use the Azure CNI overlay, but you can kind of see the differences that come in the Azure CNI overlay. We're using what's called Cilium, which is an open source project that helps with all of this, and it's another cloud native project. But over in the standard side, we kind of have to manage how our pods and our services get talked to in IP ranges, and that's really why I mentioned a moment ago why those overlays exist and whatnot. These are actually just completely two different tenants. They're not sharing the same virtual network. That's why they have the same CIDR ranges, if you were wondering about that. I'm going to stick in this auto here for a moment and show some things that are important about creating your cluster. So for one thing, these are only available in certain configurations. Have to make sure that you support things like the availability zones. So you can list your locations, and that can help you kind of decide what you're going to actually put into these things, right? So just mentioning that in case you're trying to do something like this. And once you get your cluster created, I'm not going to do that here because they do take a moment. You use this get credentials, and basically what this does is this enables us to talk to that Kube API server through kubectl or other means, and it is going to actually store those credentials in a kube config for us. So that way, what I should be able to do now, demo gods be with me, is just use kubectl directly to look at my control plane here. And for example, maybe next what we'll do is we'll go ahead and look at those nodes. And we see here, this is managed. We're in the auto, that node pool, that's letting us know VMSS that it is using a virtual machine scale set to power that node. Okay, and we can also look at our namespaces. The namespaces, like we saw a moment ago, let us know, this kube system namespace. Well, these are the pods that are running in our controller here, in our control plane, sorry. And then this is just a pod that I published, or that I ran a deployment for, but I didn't specify a namespace, so it just ended up in default. And we'll talk about what that KUARD is in a bit more. A final note, flipping back over here to Azure, is that when you create an AKS cluster, you specify a resource group, and Kubernetes itself lives in that resource group. But a second resource group gets created, right? You have less control over this, and this actually stores all those kind of backing services that I mentioned that can just kind of natively get mounted into here for us, right? So this was the non-auto one that used KubeNet. So you see we've actually got to have like some NSGs in our route table. But right there's our virtual machine scale set. So yeah, we'll compare those things more in a moment. But for now, I do want to flip back over to talking about user nodes. So like I mentioned, the system node, that's managed for you, but the user nodes, that's where you actually schedule your workloads. And they're separate from the system node, and you can even run commands on them to make sure that no user workloads get scheduled on the system node. And you can scale these node pools. The nodes go into node pools, and you can scale them independently. You can choose different VM sized based on your workload requirements. You can even leverage what are called spot nodes for cost optimization, where basically it just uses virtual machines as they're available. And if none are available at that time, like a shared VM space, then well, your services won't be able to be used. But that's how you can enable like development and test and just demo instances. Because again, system node, you're not paying for that. That's managed. Once you start adding your user nodes, that's where you start getting your cost, right? And more hints to why we might adopt something like the Azure Container Apps. We're running out of time here, so I'm going to show the commands. I'm not going to worry about running those for user nodes. But for pods, we're starting to talk about some pretty important stuff here. I mentioned they're the smallest, most basic deployable units in Kubernetes. They encapsulate one or more containers and the volumes that they might use. They run symbiotically in the same execution environment, right? They're designed to be ephemeral. So if a pod dies, Kubernetes automatically replaces it. So that way you maintain that desired state that you specified in the manifest. This approach not only simplifies the scaling management, but also aligns with those cloud native best practices for the reliability and for resilience, right? And so what I have here on the screen is an example of a pod manifest for the Kubernetes up and running demo, which if you're not familiar with this, Kelsey Hightower and some other developers from Google, Kubernetes started at Google, and they published a book called Kubernetes Up and Running, and they could basically go through a lot of what I'm talking about with you today. It's where I learned a lot of what I know about Kubernetes, and they offer this container image to be used in your deployment. So we're going to go ahead and move on to our next piece here, and maybe we'll just so going on to health checks. So health checks, there's two different types of health checks that are important to think about in Kubernetes. You have liveliness and you have readiness. They're both essential, but they do different things, right? So the liveliness check determines if the container is running as it's expected. If the check fails, Kubernetes automatically reschedules the pod to try and recover from the failure status. Whereas on a readiness check, on the other hand, Kubernetes looks to see if the container is ready to accept traffic in this place that you've specified, right? So basically, if the readiness probe fails, the pod is temporarily removed from something like a service endpoint, so that way traffic won't route to it, right? So it's one of those key things that we're building up to being able to implement these larger concepts by starting at our pods. We're defining them in that manifest, and we're even defining like what our boundaries of availability are, and how to enable fault tolerance just in that pod manifest. And another important concept in Kubernetes, although one that like you don't see directly in the cloud providers, is this concept of labels. So labels in Kubernetes are right here, these version 1 app environment right? Basically, they're a way for you to have key value pairs that attach to the pods. And they allow you to organize and group resources by these meaningful criteria. So for instance, you might assign labels such as environment production or environment test to the pods to clearly identify which environment they belong to. It not only makes it easier to find them, but it also makes it easier for Kubernetes itself to use those labels in higher level concepts like the services and the replica sets. And again, these labels, I show you here how you can actually just create a deployment without your manifest, right? So we're just running this, it's setting these number of replicas in our deployment. And so what that means is that we're actually going to have two different pods here, and each one is going to have this label, and they can participate together in like a service. So we'll see this in this next screen here, where we actually go ahead and what's called exposed deployment. And when you run those, it goes ahead and looks at whatever whatever your labels were. In this case, I'm actually using pod name, so that's not consistent between these two. But basically, the point that I want to make here is that within these services, you do this expose. It groups the pods together, and basically that's able to use those higher level concepts. And again, we'll kind of move past services and look how that gets presented in the manifest for like a replica set here. So for a replica set, instead what we're going to do is it's going to be this kind of replica set. Right here, we see that this kind is a replica set. So for the services, this is where you might see that you've got the cluster IP, or you might also see load balancer. And so we talked about on the networking side that just by specifying that in your manifest, that's able to tell your underlying cloud provider to provision that load balancer for you and to forward traffic to, in this case, we have one app, but the goal that we're trying to do now is to also make that available through something like a replica set, which we can increase our number of replicas. That takes advantage of the service, and then our traffic gets round robined across everything that we've deployed. We kind of talked a little bit about all of that stuff before. Okay, and deployments, they're built on top of replica sets. They're that declarative, they provide that declarative updating for the pods and the replica sets themselves. You basically, again, you're specifying that desired state, and then you're going ahead and letting the orchestrator do its thing. Let's revisit the Azure portal just one last time to make sure that there's nothing that I didn't mention here. So again, we got our namespaces. That cube system is where our control plane stuff is living. Default is where our actual YAMLs are getting defined. And so you can see the one, this is the cube API one. And went back too far. Here's our workloads. This is where you'll see as you create replica sets, you'll see them in here. And then we have these things called stateful sets. That's a really important concept in Kubernetes to be able to actually make a stateful application. You use persistent volumes like Azure storage, but you actually can create a stateful set, and that kind of helps orchestrate all that. Daemon sets are another really important concept. And of course, there's built-in functionality to run jobs, right? So we're kind of like making the whole gamut of things available in Kubernetes for us. And so with all these tools available, you may ask yourself, should I start using Kubernetes? I mean, as we discussed, cloud native principles are really valuable for teams aiming to deliver software rapidly and manage complicated distributed systems. Large tech companies use them. We have their testimonials about how many times a day they're deploying, how many services, and how many millions of users they have. But even if you aren't serving millions of customers, there's still a place to recognize the benefits of cloud native apps. For the apps you do develop and host, you can shift your processes to cloud native and take advantage of benefits of platforms like Kubernetes or Azure Container Apps. If you need to modernize, but you don't want to or can't handle the underlying orchestration complexity of something like Kubernetes, that's where Azure Container Apps comes into business. Azure Container Apps abstracts away Kubernetes management, so you don't need to worry about cluster setup, node scaling, or direct infrastructure patching. Some of those benefits we already talked about in the AKS automatic mode, but there are still other reasons to shift to ACA instead of AKS. I think a couple of the main features that become really attractive are, first of all, the need to not really manage too much of that Kubernetes infrastructure, but to also not really need to know how you're deploying in Kubernetes, right? Like we talked about how nice it is that Kubernetes is consistent across all the cloud providers, but you still have to learn things like the kubectl and containers to pods to services to replica sets, all that stuff, right? It still feels like you're doing infrastructure. When instead you could be focusing on what auto scaling looks like for your applications. And this is where ACA really shines. Azure Container Apps extracts away the management of those nodes. It provides a fully managed serverless environment. Instead of handling those cluster operations, what you're really focusing on are what type of software development lifecycle design patterns you want to implement. Like on the left here, we talk about the 80%, 20%, right? Like this is something that Kubernetes made easy. Like, so when those big tech companies like Netflix, they want to roll out new versions of their software, they don't just push it to everyone at once, right? They do splits to ensure that not only is the new features coming out to just a small section, but then also you can kind of just decide if you want parts of your app to actually be getting more traffic or not. So other things that might be going on are your background jobs and your queue readers. And you also get a couple benefits for things called CADA and for Dapper. So I'm going to go ahead and pull up Azure again. And what I'm going to do is I'm going to go ahead and go to the container apps. And like we mentioned, I'm going to the other one, I guess, because I know I've already got one there. So your container apps, we're kind of like leveraging the concepts of the Azure application services here. So you have this environment, right? And the environment is what allows you to create new workloads for this. So one of the things that's nice about this, and I'll show the command line equivalent of this in a second, you see we have the concepts of apps and jobs. And so if we go to create an app itself, give it a name, right? Built-in capabilities with Azure Functions. So one of the things we're going to see in a moment is that Azure Container Apps, it really doubles down on the idea of event-driven development. And so instead of you trying to process everything in your microservices, maybe you're passing things off to a queue, like RabbitMQ or some type of service bus and service queue. And then based on how many messages are in there, you can decide if you want to scale or not. And so Azure Functions, kind of like that built-in way of allowing you to automatically do things. And then with your scaling, you instead of using that HPA, use the CADA, which we're going to see in a second. So deployment source here. So you can bring your own container image or container registry from a Docker file, or you can actually just point to your source code, right? So this container image is going to allow us to deploy something like the Kubernetes up and running application, or I did have some .NET applications prepared to deploy here as well. We'll see if we can make it happen. So we're going to come into this environment. We've already got, so that down here is that environment we're talking about. We'll go ahead and create a new one just for the sake of seeing what's available here. So basic ACA environment. Okay, and we're not going to worry about making them node redundant, but it does have that built-in VNet integration that you're going to have to get you had to choose an overlay network in Kubernetes in order to get some of these enabled in an effective way. Okay, so now you can use a quick start image here, or otherwise you kind of have to specify where you're going to go. I'm going to just go ahead and use the quick start image just because we're short on time here and I want to let you guys move on from this very complicated topic. So we'll go ahead and create. And over on the code side, we're doing similar things that we had to do. We're creating our resource group, we're creating that environment instead of a cluster. And we also do have to create our own app, but you see you get some things baked in here, like your external ingress, meaning that it's going to happen externally from the container app itself. Yeah, so this is where I've specified that starter image, and basically we're just going to create the actual container app there. You come back here, the environment's spinning up. So I'll let those things finish in a second. In the meantime, let me just quickly talk again about CADA, the Kubernetes event-driven auto-scaling, and also Dapper. And that'll pretty much wrap us up. Just a few more last-minute thoughts here. So again, we're looking at that cloud native story, right? So basically, Dapper stands for Distributed Application Runtime, and basically it simplifies the microservices-based applications by kind of encapsulating how each language and each infrastructure item handles kind of service invocation and state management, and that like built-in pub sub messaging, how they manage secrets, right? These are things that typically you're writing code for, like I need to get a key, I need to get a secret from the Azure Container Vault, Key Vault. I'm going to write some code that's specific to the Azure Key Vault to get that value, right? Well, not with Dapper. Dapper basically kind of adds yet another level of abstraction around custom code for common microservice patterns. So let me see if they've got anything in here help us understand that. Well, either way, Azure Container Apps comes with this Dapper support built in, and it's kind of suggested for you to start in your journey through Cloud Native to start using Dapper to yet again abstract away from how you're using your underlying infrastructure. Okay, so there's so much more I wanted to show, but I'm just going to wrap it up here. There we go. Okay. So again, let's revisit what we talked about today. Basically, we learned about Cloud Native. We talked about what those benefits are. We saw how those principles surface themselves into Cloud Native tooling, and we started to see some of the ways that we can create those Cloud Native tools ourselves, whether we're using the Azure Kubernetes service or the container apps, which I didn't get to really demo, but it is actually quite easy to work with. Let's see, in fact, as a last minute thing, if that deployment finished. It did. So now we'll go to that container app and we'll open it up. And there we go. So just like that, this is that hello world image. So you store your own image in your own container registry, and you just tell the Azure Container App, this is the one I want to use. And they can run in those environments and kind of leverage those built-in components that we talked about. And now, one of probably the final things to mention, other than just revisiting, we've reduced technical debt, we've made it easier to focus on application features, but we're also attracting that top talent, right? People who are familiar with containers, they're learning about what's happening now. People who can use Kubernetes, they understand why orchestrators are needed. And if you have developers that are like, we're supposed to be making microservices, but they're a pain to figure out how to host, well, this hopefully kind of connects that whole story about how the software development lifecycle has evolved and ultimately how you can update your software development practices to stay up to date. So that's it for me. Thank you so much for sitting through this session and exploring Cloud Native, Kubernetes, and Azure Container Apps with me. That's all I've
Awesome
got.
work, Lee. Thank you so much. I would love if people come off mute, turn off video, give you a quick round of applause. Lee, I think you're going to make this a series. That's for sure.